Alternating currents, class 4. In this topic, I am going to discuss alternating EMF applied to pure inductor. This topic has been divided in different subtopics: expression for current, variation of voltage and current with time, phasor diagram, inductive reactance and its variation with frequency, and finally related questions.
Hello, good morning students. Again welcome in my class. In previous class, we have discussed how alternating current behaves with resistor or with capacitor. Here in this class, we are going to discuss how inductor behave with AC. How inductor behave with AC, or what will be the behavior of inductor for alternating current. Just I am recalling the behavior of capacitor with AC. In the case of capacitor, we have seen that effective opposition offered by the capacitor, writing here, effective opposition offered by the capacitor is given by Xc equals to 1 upon omega. Or we can say Xc equals to 1 upon 2 pi mu c. And we have also discussed one concept that in the case of capacitor, phase difference between voltage and current is pi by 2. And we have seen that current is ahead of EMF by pi. Now we are going to discuss the same aspect here. How inductor behave with alternating current, or we want to find out the effective opposition offered by the inductor. That we are going to denote by XL. Here it is inductive reactance. This is capacitive reactance. So first of all, we will be able to find what will be the effective opposition of the inductor. That we will discuss in this. Secondly, we will also find what will be the phase difference between voltage and current in the case of inductor, and that we will get as minus pi. Just in the proceeding of class, we will discuss that here current will lag behind the EMF by pi. So these two aspects we will discuss in this class. So let us suppose this is a pure inductor which is connected with an alternating source. Here why we are writing it is pure inductor, because every inductor is made of some metal coil, or we can say copper coil, and copper is having finite resistance. It means every inductor will have some resistance, but here we have discussed that the resistance of this inductor is almost zero. It means we are discussing only its inductive effect. So let us suppose this is an inductor having inductance L, and it is connected with an alternating source of EMF V equals to V naught sin. V equals to V naught sin. We know that whenever inductor is connected with variable source of EMF, or we can say alternating source of EMF, then there will be some induced EMF. Therefore, if we apply Kirchhoff's law here, then we can say V is the applied voltage, and induced EMF in the case of inductor will be minus L di by dt, and that will be zero because there is no any resistor. So therefore, if we apply the Kirchhoff's second law, then voltage applied is V, induced EMF is minus L di by dt, and since there is no potential drop across resistor, therefore it becomes 0. V minus L di by dt equals to 0, and then like L di by dt can be written as V, or which can also be written as V naught sin omega. That we have written. L di by dt becomes V naught sin omega t, and that implies di equals to V naught by L sin. And therefore we have to find out I. I will be equals to V naught by L constant and integration of sine omega t, or that will become V naught by L as it is. Integration of sine omega t will be minus cos omega t upon omega. Integration of sine omega t will be minus cos omega t divided by, and now we have to arrange this equation. Then applies I equals to V naught by omega L. This quantity we are writing separately, and here it becomes minus cos omega. Now here it is sine omega t, here it is cos omega. One is sine omega t, other is cos omega t, and we want to compare the phase. We want to compare the phase. Therefore, what we have to do? We have to convert this sine omega t factor, and here it is cos omega t. These both functions should be same. Then and then we can compare the phase. Therefore, I am writing it as this V naught by omega L. We can write I naught. Just in the previous class for capacitor we have written V naught by omega L, that we are writing I naught. So definitely you are understanding. This quantity will have the dimensions of resistance, and this quantity is known as inductive reactance. Just we will discuss. Minus cos omega t, this I am writing minus sine pi by 2 minus omega t, because we know that sine 90 minus theta, that is cos theta. So here we are writing cos omega t as sine 90 minus theta, and other component we also, other factor we also know that sine theta is an odd function. Therefore, sine of minus theta can be written as minus. Sine theta is odd function. Therefore, sine of minus theta can be written as minus of sine theta. Therefore, how we will change it? I naught this minus sign as it is, and we can also write minus sine omega t minus pi by 2. I think you are easily understanding. Here it is pi by 2 minus omega t, and here I have written omega t minus pi by 2. Therefore, this minus can be taken out, and this minus minus will become plus. Therefore, the final answer we will get I was to I naught sine omega t minus pi. This is the equation for. In the case of capacitor, we have seen that I was to I naught sine omega t plus pi. But in the case of inductor, it is clear that I equals to I naught sine omega t minus pi by 2. It means in the case of inductor, current lag behind the EMF by pi by 2. In the case of capacitor, current is ahead of EMF by. Again, I am discussing this once again. Di equals to V naught by L sine omega t dt. V naught by L integration of sine omega t, that is minus cos omega t by omega. And now by making slight changes we will get. Now we will discuss this part. Since V equals to V naught sine omega t, I equals to I naught sine omega t minus pi by 2, it means it is very clear that there is a phase difference of pi. Therefore, we can say pi equals to minus pi by 2 for inductor. Phi is minus pi by 2 for inductor. Therefore, if we draw the phasor, diagram for this, let us suppose this is the phasor for voltage V naught. Here it is omega t. Omega is angular velocity of rotation, t is the time. Then projection of V naught on this axis, or we can say component of V naught along this axis will be V naught sin omega t, and that we have represented. But here in this case, current lag behind the EMF. In this case, current lag behind the EMF by pi by 2. Therefore, the phasor for current will be like, and this angle will be 90. So this is the phasor diagram for voltage and current. Here we can mark as T. This is vision. On this side, we will get the component of V naught sin omega, and in this side, we will get I naught sin omega t minus pi by 2. It means here from this phasor diagram, it is clear that voltage and current both are not in phase, or we can say there is a phase difference of pi. Here current is lagging behind the voltage by pi. So that is the basic difference between inductor and a capacitor. Now we are discussing this quantity. Here I naught we have written as V naught by omega. So definitely it is clear that V naught by omega L. It means this quantity will have the unit of resistance that we can write as ohm. And since omega L we are writing as ohm, it means omega L is the effective opposition. Omega L is the effective opposition, and this we are denoting like XL equals to omega L equals to 2 pi nu L, or XL equals to omega L equals to 2 pi nu L, and this is known as inductive reactance. This is known as inductive reactance. How we can define inductive reactance? Effective opposition. Effective opposition offered by inductor in the flow of current is defined as inductive reactance. And from this diagram, it is also clear that XL depends upon frequency, but the dependence of frequency and XL is different as in the case of capacitor. In capacitor, XC is inversely proportional to frequency, but in the case of inductor, XL is directly proportional to frequency. That is the basic difference between inductive reactance and capacitive reactance. So this is basic difference between capacitive reactance and inductive reactance. XL equals to omega L, while C equals to 1 upon omega C. Now we will discuss the behavior of this inductor at different at very high frequency. It means the value of frequency is very high. At very high frequency, we can generally assume, let us suppose, nu tends to infinity. Then XL tends to infinity, and therefore inductor behave like an open circuit. Since the effective opposition become infinite, it means there will be no current. Therefore, at very high frequency, inductor behave like an open circuit, or we can say it will not allow any current to pass through it at very high frequency. At very low frequency, we can say nu tends to 0, and therefore XL tends to 0, and we can say the inductor will behave like a short circuit. Pay attention. Wherever we are writing open circuit, it means the opposition of circuit becomes so high so that there will be no current. That is made by open circuit. And whenever we are writing short circuit, it means the resistance of the circuit is so small that there is very large current through the circuit, or that is known as short. And now finally, if we talk about DC, this means direct current. For direct current, frequency is exactly 0, and therefore XL equals to 0. It means for DC, again the inductor will behave like short circuit, or we can say it will offer no resistance or no hindrance or no opposition to the flow of DC. In the case of DC, nu will be 0, therefore XL is 0, and hence it will offer no hindrance, no resistance, no opposition to the DC. So this is what about the alternating EMF applied to pure inductor. Now we can summarize these three main aspects: how resistor will behave for AC, how inductor will behave for AC, and how capacitor will behave for AC. And we have to keep in mind 2-3 main key points related to these topics, because these three topics are very important. Therefore, conclusion of these three topics: how resistor behave with AC, how inductor behave with AC, how capacitor behave with AC, what will be their phase difference, and what will be their effective opposition. These points we have to remember clearly. So this we can summarize in the form of a table that will be important for you. This is resistor, this is inductor, this is capacitor. Here we are writing phase difference. Here I am writing phase difference between voltage and current, that is phi. And here we are writing effective opposition. Effective opposition. In the case of resistor, phase difference phi equals to 0. In the case of inductor, phi equals to minus pi by 2. And in the case of capacitor, phi equals to plus. So these are the values of phase difference. Now effective opposition. Here effective opposition will remain same, and that is R, that is known as resistance. In the case of inductor, the effective capacitance, effective opposition is denoted by XL, that is known as inductive reactance, or it is denoted by omega. Or we can say it depends upon frequency, it is directly proportional to frequency. In the case of capacitor, here the effective opposition will be capacitive reactance, it is having value 1 upon. Now it is very clear that resistance, inductive reactance and capacitive reactance both will play, all will play the role of effective opposition, and these all are having value of. Okay. So this is the what summary about the inductor, capacitor and resistor, how they behave with this. Now we are discussing some very important questions related to this topic. Let us suppose a bulb is connected with a capacitor. Let us suppose a bulb is connected with a capacitor and the combination is connected with alternating source of EMF. This is question first. A bulb is connected, this is a bulb. It may have some resistance. A bulb is connected with the help of a capacitor. And both are connected in series, it is very clear. And we know that bulb is having some resistance R. Just we have seen that capacitor will also offer some hindrance or some opposition or obstacle in the flow current, but that will be Xc. The hindrance of this capacitor will be Xc, or that we can write as capacitive reactance. The question is that initially the bulb and the capacitor are connected in series with the alternating source of EMF, and the bulb glows with some brightness. Bulb glows with some brightness. That is the question. Bulb is connected with the capacitor and it is connected with alternating source of EMF, and the bulb glows with some brightness. How? Question is this: how brightness of bulb changes? How brightness of bulb changes if, now there may be number of questions. How brightness of bulb changes if, number one, frequency of AC is increased. Frequency of AC is increased. I will directly write the answer here. The question I am repeating again. A bulb is connected with a capacitor in series and they are connected with an alternating source of EMF. How brightness of the bulb changes if frequency increases? Now we have to see, if frequency increases, we know that on R there will be no effect, resistance में कोई effect नहीं होगा. Xc, it will change, since Xc equals to 1 upon omega c, or we can say 1 upon 2 pi mu c. Therefore, as frequency increases, Xc will decrease. Since Xc decreases, it means effective opposition decreases. We can say effective opposition decreases, and therefore current increases. And if current increases, then brightness will also increase. So this is the first question, that is very important question. What question? Frequency increases, then Xc will decrease, therefore effective opposition will decrease, hence current will increase, and consequently the brightness of the bulb will also increase. Second part, a dielectric slave. Dielectric slave is introduced between the plates of the capacitor. A dielectric slave is introduced between the plates of the capacitor. Then, if dielectric slave is introduced, we know that whenever dielectric slave is introduced, then capacitance will increase. The amount of increase will depend upon the dielectric constant, but definitely the capacitance will increase. If capacitance will increase, then Xc will decrease, because Xc equals to 1 upon omega c. So capacitance increases, Xc decreases. Xc means effective opposition of the capacitor, and since here it is resistor and capacitor, in resistor there will be no change. Here effective opposition decreases, therefore total effective opposition also decreases. Finally, current increases, and we can say brightness also increases. C part, we can say, if area of plates of the capacitor increases, area of plates of the capacitor increases, since C equals to epsilon naught A by D. Area increases, C equals to epsilon naught A by D. Area increases, therefore C will also increase. And since C increases, the whole effect will remain same. It means again Xc decreases, effective opposition decreases, I increases, and brightness increases. It means what will be the final answer? Brightness will increase. I have written here 2-3 steps directly. C increases, therefore Xc decreases, Axis decreases means effective opposition decreases, therefore current increases, hence brightness will increase. D part we can say distance between the plates of capacitor. Distance between the plates of capacitor become double. Distance between the plates of capacitor become double. Now the effect will be quite different since C equals to epsilon naught A by D. We have doubled the distance, or we can say we have increased the distance, therefore capacitance will reduce. If capacitance will reduce, then capacitive reactance will increase. Capacitive reactance will increase, and if capacitive reactance increases, effective opposition increases, therefore current decreases, and consequently the brightness will also decrease. So this is the effect of change of distance d. Now we can also use this equation. AC is replaced by DC. It means instead of alternating current, we have used direct current. We know that for direct current, frequency is 0. For direct current, frequency is 0. Therefore, X equals to 1 upon omega c. X equals to 1 upon omega c, that will become infinite. Hence, the circuit will behave like open circuit. Therefore, no current. Or we can say bulb will not glow. Bulb will not glow. So this is the effect of different parameters on the capacitive reactance or inductive reactance of inductor or capacitor, depending on the situation. So in this question, we have discussed how capacitive reactance changes with different current, and consequently it will affect the brightness of the bulb. Similar question we are discussing again. I think you all are able to understand this topic very clearly. Next question I am discussing. A bulb is connected in series with an inductor. A bulb is connected in series with an inductor. R is the resistance of the bulb, and is the inductance of the inductor, and it is connected with an alternating source of EMF V equals to V naught. The question is similar. The bulb glows with some brightness. Initially, the bulb glows with some brightness. How the brightness of the bulb will change? The question is this: how brightness will change? How brightness will change? First question, or first part. If inductance of the inductor increases, that question. If inductance of the inductor increases, since XL equals to omega L, as L increases or as inductance increases, XL will also increase. XL increase, it means effective opposition of the circuit will also increase, and consequently current will decrease. Consequently, current will decrease, and finally we can say brightness will also decrease. So in this case, the brightness of the bulb will decrease. Second question here. if frequency of the AC is reduced, how the brightness of the bulb will change if frequency of AC is reduced. Since frequency is reduced, therefore XL equals to 2 pi nu L will decrease. XL equals to 2 pi nu L will decrease. Since XL decreases, therefore effective opposition will decrease. Effective opposition decrease, consequently current will increase, and therefore brightness of the bulb will also increase. So in this first part we are increasing inductance L. Here frequency of the AC is decreased, and since frequency decreased, therefore L will decrease, effective opposition decrease, current increase, and finally we can also say brightness increase. We can consider so many questions depending on this type. One question I am again including. AC is replaced by DC. AC is replaced by DC, so nu equals to 0, and therefore XL will be 0, and hence the bulb will glow with maximum brightness. Bulb will glow with maximum brightness. In this case, since XL will be 0, therefore the bulb will glow with maximum brightness. So by using the formula, we can solve this type of questions very easily. Now the third question, again very easy question, but very important question. Identify the circuit elements. Identify the circuit elements. How we will identify? One graph is given. Here it is nu. It means variation of frequency versus opposition, or we can say effective opposition. Having unit ohm is given. Effective opposition is given, the variation frequency is given. The graph is like this. One graph is for this, other graph is like this, and the third graph is like this. And we have to identify the circuit element 1, 2, and 3. Question is very easy, very conceptual question. If we see this first element, we don't know what is the name of this first element, but we can identify this. For element 1, the graph is straight line having some slope. It means opposition is directly proportional to frequency. For graph 1, opposition directly proportional to frequency. And now we can recall there are two formulae. One is XL equals to omega L, or XL equals to 2 pi nu L. Other is XC equals to 1 upon 2 pi nu C. Since opposition is directly proportional to frequency, therefore it will be inductor. Because for inductor, XL equals to 2 pi nu. And therefore in the case of inductor, the graph between opposition and frequency will be straight line passing through the origin. So the first one is inductor. For element 2, the graph is like this. It means it is very clear that here opposition is reciprocal of frequency. And now I think you all might easily understand that this element is capacitor. This element is capacitor, because for capacitor XC equals to 1 upon 2 pi. And the last one, I think without solving you can easily identify. It is unchanged or it is not changing with frequency. It means the third is for element third, no change with frequency, no change in opposition with frequency, therefore it is resistor. So now we can easily identify this one is resistor, this is capacitor, and this is inductor. So this is the role of opposition with frequency. For inductor, opposition varies directly with frequency. For capacitor, opposition is reciprocal of frequency, and for resistor, the opposition will remain same. There is no change of resistance with frequency.